Okay, so after this chapter is over, I think you'll really enjoy the lab I have set up for you. It actually takes me about an hour and a half just to set up the lab. I have to make some solutions, stuff like that, but you'll probably spend 4 days, 3 days doing the lab, 1 day writing up the lab with your partners, answering questions, that kind of thing. And then on the lab, it's not really one lab, it's actually like 7. It's like one lab with 7 reactions, and you'll go around the room doing these different reactions. And when this chapter is over, I think you'll really understand what's going on those reactions like that. Okay, so the chapter is called Reactions in Aqueous Solutions, because number one, much of chemistry is not done where you lay a solid chemical on top of another solid chemical. Very, very little chemistry is like that. Most of the time, you have solutions of things, and then they react in a solution because they're bouncing around, stuff like that. So that's a lot of chemistry is solution chemistry. All right. So what we're going to do is, and if you didn't write this in your book yesterday, I like to author this book, but I truly would have put these 2 or 3 pages in this chapter. I would have done it. Maybe he thought the chapter was already hard enough. I don't know. But I'm going to add pages 452, maybe 454. So let's go back there one more time. And this will be the last time I teach that. If you were here yesterday, you'll hear it again. There you go. All right. So let's go to 452. And I know there's a lot of writing on this page, but your page is kind of blank. And if you neatly want to write in your book, it doesn't bother me if you want to neatly write some things in there. But in order for us to understand this chapter, we have to understand the nature of water. And I told you yesterday about how I feel differently after I became a believer, how much differently I started thinking about water as being kind of God's gift in the small molecule world. I think carbon and hydrogen are kind of the gifts in the atomic world. And I also think that hydrogen or water is kind of the gift in the small compound world. But water shouldn't act like it does. And I mentioned this before, and yet it does. Water is very unique. It has a set of properties that make everything happen. They make lots of things happen on the earth. Okay, let's take a look here again. First of all, water is made of 2 H's and 1 O, and these are all nonmetals. So what kind of a bond would you expect to have there? Okay, they would be called covalent bonds. And matter of fact, there would be a covalent bond here and a covalent bond here. Everybody got that? Pretty easy. Now, there are many 3-atom molecules in nature that are linear. The most famous would be carbon dioxide. Carbon dioxide is linear. It's C, double bond O, double bond O. It's linear. It's a straight line. If water had been linear, all this great stuff wouldn't have happened. God bent it. It's a bent molecule, about 105 degrees angle. You see that? Now, the next thing that happened was that when they share, a covalent bond means one of your electrons and one of my electrons, that's a pair. We're going to share that pair of electrons. Got it? Now, God made it so that some elements are greedy. Some elements are more electronegative, which means when we share electrons, they're going to spend more time around oxygen than they do hydrogen. And the same thing is going to happen here. You see that? We also mentioned yesterday about, and that's a quick lesson, how many electrons does every atom of oxygen have? How many electrons does every atom of oxygen have? Everybody. 8. That's why it says 8 protons, 8 electrons, right? It's a neutral atom. Now, of those 8, how many are in the first energy level, how are in the second? I think you had this in 9th grade or 8th grade. But I happen to know that oxygen's in period 2, so I know it has electrons in the first and the second energy level, right? And the first one, I can only hold 2. So he must have 6 in the second. Another little clue to me is that little Roman numeral there, 6. See that little six there? I know it has 6 valence electrons, 6 electrons in the outermost energy level. I also know, except for helium, when elements get 8, when they get 8 in their outermost energy level, they stop reacting. So oxygen will react because he doesn't have 8. He would love to have 2 more. If he was neutral and he picked up 2 more electrons, he'd become -2. And that's what you did when you did compounds, right? Oxygen has a -2 charge in a compound, and now you know why. He likes to gain 2 negative electrons. Now, hydrogen only needs to gain 1 more because the first energy level can only hold 2. So hydrogen wants to gain 1. Hey, I want to gain 1. Well, I want to gain 2. Okay, well, let's at least help each other out a little bit. And hydrogen gets his own and yours part of the time, so I got my 2. And another hydrogen has to come along, and that's why water only has 2 H's. It didn't have 3, doesn't have 4, it's only 2. Okay, that was a quick story. All right, so anyway, they're not sharing equally, and the electrons spend a lot more time around oxygen than they do hydrogen, so that causes something very, very special to happen. This molecule itself becomes polar. Polar meaning having opposite ends. And so the oxygen end, where the negative electrons spend more time, it's going to tend to be a slight negative charge, and the hydrogen is going to be slightly positively charged, and that's called a polar molecule. Okay, so let's get down to some details. What is the intramolecular bonding for water? What is the intramolecular bonding for water? What's the name? What kind of bonding is found within a single water molecule? Everybody. What is it? Uh-oh. What do you think? Raise your hand if you know it. You just don't say anything. Okay. Oh, that's bad. That's bad. Okay, one more time. What is the bonding, the intramolecular bonding for water? What kind of bonds? What? No? What? They're covalent. Isn't that right? Now, because they're sharing the electrons not evenly, they're not sharing evenly, we have a special name for that. They're called polar covalent bonds. Polar covalent bonds. Uneven sharing. Okay, now, that at least tells me a story about each water molecule. But also, there's some weird things that happen with water, and it's because it's polar. So we go down here, and this is all review from yesterday, I thought. And if I have one water molecule here and I have another one here, will there be any interaction between water molecules? Could there possibly be an intermolecular bonding? And Tyler knows. What's the name of the intermolecular bonding for water? Hydrogen bonding. And so hydrogen bonding occurs when the slightly negative end, the oxygen end of water, is going to be attracted to the hydrogen end of another water molecule, and et cetera, et cetera, et cetera. And that makes water ball up. If you put a piece of water on a table, you'll see it kind of form a ball, doesn't it? They're pulling each other. If you've ever seen insects like water striders, why don't they sink in the water? How is it that you can actually put a needle? I've done this before. You ever laid a needle on water, it didn't sink? Now, what is that forms that kind of a skin, or what makes you be able to fill a glass of water higher than it can hold? What is it? One more time.
Surface tension?
Well, it's surface tension, right. And surface tension is because of what? Hydrogen bonding, okay? I told you a story yesterday also that I don't think Ms. Founds would have said this, but God, when he made DNA, he wanted the rails of the ladder that would hold the A, the T's, and C's. He did not want them to be scrambled, so he made the rails of the ladder have strong covalent bonds on them. But he also made it so that one piece of DNA could be unzipped from another, because what kind of bonding holds A, it makes A attract to T, or T attract to A, or C with G? That's called hydrogen bonding. And so that's not as strong. So DNA can be opened up. and you can make a new copy, or it can be closed back. DNA can be opened up, and you make a messenger RNA, and then closed back. Do you remember all those stories? DNA, remember that? Okay, well, anyway. So, anyway, hydrogen bonding explains lots and lots of things. Now, I don't think I did this for your class. Did I talk about water being a liquid at room temperature yesterday? One class I did, and one I didn't. Okay, let me get into that. This is the hardest thing I'm going to talk about today. We have, I don't want you to necessarily know this. We do this in physics class, but there's a mathematical equation for kinetic energy. Does anybody know what kinetic energy is? Do you have that somewhere in middle school? I bet you did. Yeah, energy of motion. Is that right? And so I don't know what that means, but energy of motion. Yeah, if I throw a baseball at 30 miles an hour and I throw the same baseball at 50, don't you think the one at 50 is going to have more kinetic energy? So I know that velocity has something to do with it. Velocity has something to do with kinetic energy. What if I throw a 5-pound rock at 50 miles an hour and I throw a 10-pound rock at 50 miles an hour? That would break my arm probably. Which one would have more kinetic energy there? Hey, you know what? I think mass has something to do with kinetic energy. Well, somebody's figured out the mathematics. It says kinetic energy is 1/2 mass times velocity squared. Okay, all I want you to know is every particle that's above absolute zero, and we all are, we're all above absolute zero, every atom in you, every compound, everything has kinetic energy. It's moving. It's moving, okay? And if you took something like ice, it would move a certain way, and if you turned it into a liquid, it'd move a little bit faster. It'd have more kinetic energy. If you heated it some more to a gas, it might have a lot of kinetic energy. See that? Okay, now the reason I'm telling this story is that I told you water was so special. I want to show you something here. If I look on a periodic table, and I'm looking for the gas called hydrogen gas, if I look up there, here's how much it weighs. Each hydrogen weighs about one atomic mass unit, okay? So H2 would weigh 2. Well, guess what? At room temperature, that mass is so tiny that the speed of hydrogen is really fast. It's so fast, there's no way it could hold itself as a solid or liquid. Hydrogen's got to be a gas. It's got to be a gas. Let's go up the ladder a little bit here. How about ammonia? Ammonia is NH3. This weighs 14. Each of these weigh 1. This weighs 17. That's a whole lot heavier. Now, at room temperature, if you're heavier, you won't move as fast. But guess what? It moves fast enough that ammonia is going to be a gas. Let's move the ladder a little bit more. Let's go to 28. Let's go to nitrogen gas, the stuff you're breathing right now. It has a mass of 14 plus 14, 28. That's heavy. That's heavier than 17. It should be a little slower. But guess what? How slow is it? Slow enough to be a solid? No. Slow enough to be a liquid? No. It's got to be a gas. It's got to be a gas. What's above 30? How about O2? How much did it weigh? 32. Solid, liquid, or gas at room temperature? Gas. Okay. All right. Well, carbon dioxide. There you go. Carbon dioxide. Look at that. Oh, 44. It weighs 44. 12 plus 32. It's 44, right? Now that's going to be even slower. Is that going to be a liquid or a solid? No. This is too much kinetic energy for something of that mass. Let's jump all the way up to this guy called butane. Butane's a gas, and it has a mass of 58. 58! What is it at room temperature? A gas. Okay, I get it. You got to be a much, much heavier than this to be a liquid or a solid at room temperature. All right, what is the mass of water? Look on a periodic table so you can figure it out before I tell you. What's the mass of water if I said in AMUs? What do you think? How much? 18. Each oxygen is 16. Each hydrogen is 1. That's 18, right? Look at me. Look in this chart. 18. You must. Water must be what? There is no way that should exist. There is no way you should be a liquid. There's no way. Nothing else with that mass is a liquid, but water is. That shouldn't happen. Of course, if it didn't happen, you wouldn't be here. It does happen. What do you think is that extra force that says you're supposed to be a gas, but something must be pulling you together so you won't be able to turn to a gas until I heat you quite a bit? Raise your hand if you know. You just don't want to say. How many? Raise your hand if you think you know. What is that extra thing? One person. Two people. Why? What is holding water together? You should be a gas. No, something's keeping me from turning into a gas. Two people? That's all? All right. Max, what do you think it is?
The hydrogen bond?
Yes. And again, you wouldn't have hydrogen bonding if water wasn't bent. You wouldn't have hydrogen bonding if oxygen wasn't more electronegative and greedy. See that? This is, I don't know, maybe I'm trying to be too dramatic. This is amazing to me. And I'm going to show you something else. We did this yesterday. Why is it that a lot of ionic compounds can be dissolved in water? What is it that water can do that could dissolve something like NaCl or calcium chloride or potassium hydroxide? Why can it dissolve so many ionic compounds? And if you think about it, water has a plus-minus nature. It's polar, isn't it? And what about an ionic compound? What does it have? What are ionic compounds made of before you put them in water? This is a big part of this chapter. What are they made of before you put them in the water? Starts with an I. Ions. They're only made of ions. There are no neutral atoms in an ionic compound. So they're made of ions before you put them in water, and then water has the ability to, well, I always ask this question on the test, which end of water will be attracted to the negative ions in an ionic compound? Which end of water is attracted to the negative chloride ions in sodium chloride? Let's see, chlorine, they're negative ions. So which part of water is positive? The hydrogen end. And if you look here, look at the drawing. You see how they show the hydrogen end of water being attracted? So when enough water goes around that chloride ion, it pulls it out of the crystal in maybe like a 10,000th of a second. And then what end of the water molecule is attracted to the positive sodium ions? Look at the drawing. Well, sodium ions are positive. So which end of the water molecule is negative? And that's the oxygen, isn't it? That's why you see that drawing. Okay. All right, we'll move on now. Let's go over here. Okay, so I get it. The ionic compounds have a plus-minus nature, and water has a plus-minus nature. Likes dissolve likes. I get it. And so polar things tend to dissolve ionic compounds. How about this right here? This is not an ionic compound. How do I know? Because it's made of a non-metal. This is called alcohol. This is ethyl alcohol, okay? You know it's an alcohol because it has a carbon, oxygen, hydrogen. It has a COH. See that? So it's an organic molecule with a COH. If you were an organic chemist, if you're a first-year chemist, you would write it as C2H6O. You know how an organic chemist would write it? CH3, CH2, OH. And that's the way they write, because they let you know that I have a COH at the end, I'm an alcohol. And that's why they do that. Now, what happens when O and H form a bond here? Even? Are they going to evenly share the electrons? No. That sets up a polar bond again. Another polar bond. And so this end of the alcohol is going to be polar. Will water dissolve alcohol? Will alcohol dissolve in water? What do you think? Likes dissolve likes. Water's polar. Alcohol is polar. What do you think? Yes. And I even told you the story about, I have some rubbing alcohol in there. It says 70% rubbing alcohol. Oh yeah? What's the other 30%? Water. Where is it? It's dissolved, isn't it? Okay. let's go down here. How about something that's not an alcohol, but something like sugar? The kind of sugar you have in your house is called C12H22O11. And all you know is that it's going to be covalent bonds all over the place, right? Here's what it actually looks like. Now, if you take a look, COH, there's a whole bunch of these OHs here, aren't there? And so you're going to have a polar bond here and here and here and here and here. So there are many places on this sugar that are going to be polar. Do you think sugar dissolves in water? Well, now you know why. Now you know why. Because it's a polar molecule. Last but not least, and I'm going to go to the other part of the chapter. What if you had something that was only made of carbon and hydrogen? That's actually a fairly even sharing. They sort of evenly share the electrons that they're sharing. And so I would expect that to be a non-polar molecule. What happens when you put non-polar things into polar water? Will they mix? They won't. And that's where you get that thing like vegetable oil and water, and they won't mix. They'll form a layer. Vegetable oil is less dense, so it'll sit on top of the water, but it won't mix. Gasoline, it'll sit on top of water, but it won't mix. Yes, no? You ever see movies where some ship got torpedoed, and maybe the diesel fuel, which is also a hydrocarbon, diesel fuel's all over the ocean. And what sometimes happens, even though it's the ocean, what sometimes happens? They catch on fire, don't they? Because the diesel fuel is floating on top of the water. It won't mix. It won't mix in the water. All right, do you have any questions? That'd be the second time you heard that story, and I probably won't go back to that again, but I just want to make sure, if you understand the nature of water, I think I can teach you the rest of this chapter. Okay, let's go back. Okay, so here we go. It says here, remember we had these things called driving forces? Without looking, can you list the 4 driving forces we talked about in class? Without looking, just raise your hand, give me one. How about that? Just give me one. Something that's going to make the reaction take place. It's called a driving force. All right, what do you think?
Formation of a solid.
Right. That means that I might start with 2 things that look like a liquid. I can't see any solid. When I put them together, a solid forms. That's great. What's another one? Yes?
Formation of a liquid.
Yes. That means that I might have 2 solutions, and there might be water already there. When I say formation of water, I mean new water. Like an H from over here and an OH from over here, they get together and make new water. Another one. Formation of a gas. Now this, even though this has to do with thermodynamics, and I'm not going to get into that, here are these liquids, and then this gas can be formed. That seems to be a driving force to make things happen. Again, that has to do with disorder, entropy. I'm not going to get into that. And one more. One more, very hard to see. Okay, now in this chapter, the hardest thing for you to learn will be the transfer of electrons. And I'm going to save that near the end, okay? But where somebody says, I'm going to gain 2 electrons because you're going to lose them. If you're going to lose 2 electrons and I'm there to gain them, then we're going to have a reaction take place. But I also tell you that not all reactions have electrons being transferred. So that's what we're going to learn today, okay? Well, let's take a look at, let's go over here first. Before I get into the driving forces, he wanted to stick this picture into your book. And it used to be, a long time ago, that kids at home, they might actually do this at home. They might do something like it at home. They might actually, believe it or not, get a battery out and get some wires out, and they might even have a little light bulb here. It wouldn't have to be a big light bulb. It could be a little one. And then they might actually touch the wire to the battery, light bulb, and then they might actually touch the wires and say, the light bulb comes on, They make a complete circuit. Remember that? Now, unfortunately, I don't think your age, that may not even occur. You don't even have to raise your hand if you've done it. I've done it. But have any of you ever made a circuit with a battery and a light bulb? Have you done it? It's a shame if you haven't. It's like, what? You've never made a complete circuit where a motor goes on or a light bulb goes on. And I hate to say it, but you should do that sometime. Now, if you do that, you would know that what if I had these two pieces of wire, if I wanted them to touch, the light bulb would come on. I could also hook it onto a thing called a switch. A switch would be a little piece of metal. And it says, when do you want the light bulb to come on? When this piece of metal touches this one. That's called a switch. And if you've never done any of this, then this picture doesn't mean much to you, but you could do something like this. I've had people do this for extra credit. Everybody has old Christmas lights that they think don't work anymore. You could actually cut those out. Cut them out and have little wires come out of it. And probably the ones that didn't work on a battery, they won't work. But a lot of them still work. It's just that somebody in that chain doesn't work. Get it? Anyway, so what if you were to do something like that? Have a little Christmas light and a little battery, and you have the two wires like this, and what if you were to touch them and the Christmas light came on? Good. What if I touched them to a piece of metal, like an aluminum can? What do you think would happen? Would it conduct electricity and complete the circuit? Yes. Almost every metal I know of conducts electricity. Now, let's go over here now. What's this picture showing? This picture is showing a beaker with, instead of just wires, they just put some big pieces of metal in there called electrodes, just makes it so you get more contact. What if you were to touch these two pieces of metal together? Would the light bulb come on if I touch this piece of metal to that one? What do you think? Would the light bulb come on if I touch this to that? Let's see, complete circuit. Yes, okay. But it's not coming on right now. Why is it not coming on right now? What is it in? What are the two pieces of metal in? What is it in? Now, you may not know this, but the stuff that comes out of this faucet is not pure water. The stuff at your home is not pure water. You can buy it. You can buy distilled water. You ever seen that? It's actually pretty cheap. I'm surprised how cheap it is. Pure water, distilled water, has only water in it. It only has H2O. H2O. Now, even though each piece of water has a slight positive, negative end, the charges don't travel from one to another. And so, does pure water conduct electricity? And the answer is no. Well, guess what? Water then is called a non-electrolyte. An electrolyte, and I don't know why the author didn't write this. I have every one of my students try to write this in the book. What is the definition of an electrolyte? An electrolyte is a solution that conducts electricity. Get that? So what they're doing here is figuring out who's an electrolyte and who's a non-electrolyte. All right, so pure water is a non-electrolyte. Okay, good. What if I put my apparatus into salt water? Now, be careful. It says NaCl aqueous. What do you think is in that beaker? Starts with an I. Ions. What was NaCl made of before I put it in water? Ions. So what happens when I put it in water? The ions separate, don't they? Now I have these ions moving. They're free to move. They're free to move. And the ions can actually take a charge from one electrode to the other, and it's as if you were touching a piece of metal. It completes the circuit, and we say that salt water is what? What's it called? An electrolyte. Maybe you remember, if you have any little brothers and sisters, because you may not remember yourself, one of them got sick, or you got sick, and maybe you had a fever, and maybe you called the doctor, maybe you went in the doctor, and they say something like, make sure they get a lot of electrolytes. Oh, okay. Where's the electrolyte store? You know, where do you go to get electrolytes? Did you know that in soft drinks have electrolytes in them? Powerade, everybody know that? It is. If you want to spend more money, you can go to the store and they have a thing called Pedialyte. Pedia, that means children. Light, electrolyte, good name. Pedialyte. You just pay a lot more money for things that have sodium ions in it, potassium ions in it, chloride ions in it. That's what you're drinking. So you could just drink some Powerade or even soft drinks and you would get electrolytes. Your body runs on ions. My nerves, my brains, they run on ions. My muscles, they run on ions. And so you need electrolytes to make your body work all the time, okay? So now let's go over here. Here's a hard question. What if I made sugar water? What if I made sugar water? I just got done describing to you why sugar dissolves in water. Will it be an electrolyte? Is sugar water an electrolyte? All right, Ty, I haven't talked to you all day. What do you think? This is a hard question. Do you think sugar water is an electrolyte? He says, well, a 50-50 chance, as long as he doesn't ask me to explain my answer. What do you think?
Yes.
Yes, and why do you say that? Okay. How many people say yes? Raise your hand. Sugar water is an electrolyte. Keep a little bit higher. Okay, how many people say no? All right. Why do you say no?
I don't know.
Okay, why do you say no? What is it? It's not ionic. How do you know that? Right, non-metal, non-metal, non-metal. It dissolves in water because of polar nature, but is it made of ions? No. So if it dissolves, there are no ions. So you got pure water and no ions. This is a non-electrolyte. Get that? Now the reason I keep mentioning that, and I think I know why the author wanted to bring this to your attention. You're going to see page after page in this chapter. Look, beaker with little balls in it. Beaker with balls in it. Beaker with the balls in it. What's the point? They must be having some kind of point they're trying to make. There's a more beaker with the balls in it. And here's what makes this chapter hard. Here's what makes this chapter hard, okay? Take a look right here, and I'm gonna zoom in on that a little bit, okay? Look right there. Okay, they're gonna react. Let's see, who can I call? Danielle. Danielle, read this to me in English, okay? Got chromium in it. Yes. Reacts with. Yes. Is that right? Now, did we do something like that last chapter? And this is going to be a double replacement reaction. Is that correct? Okay, now, Daniel did so well. You did so well. Tell me the two products. Say it in English. What are the two products going to be? Yes. That's right. That is correct. Now, I didn't print one of these out for you yet. I will. I'll probably do it tomorrow. But there's a chart right over here. I know you can't see that very well. See that little chart right there? Okay, I'm going to give you your own copy of that. And that's called a solubility chart. Okay, now let's take a look right here. Is potassium chromate soluble in water? What does AQ mean? It's dissolved in water. If it's dissolved in water, is it soluble in water? Yes. What about this other guy? So if I saw this experiment, I'd have a beaker that looked like water and another beaker that looked like water. But what's really in those beakers? And that's what the author's trying to get you to say. What's really in this beaker right here? What do you think? Let's go over here this side of the room. Jonathan, what is in this beaker of potassium chromate aqueous? Potassium what?
And chromate and water.
Sort of. Otherwise, see, the author wouldn't keep drawing these beakers with little balls in them if that's all it was. What's really in that beaker? It's not potassium chromate. Now, we called it potassium chromate before I put it in the water, and I still call it potassium chromate aqueous after it's in the water, but what's actually floating around? I'll give you one more chance. What's actually floating around in that beaker?
Potassium.
Say it. Potassium what?
Ion.
Yes. And what else?
Chromate. Ion.
Yes. And there are twice as many. Yes. And so this will break up into 2 potassium ions and 1 chromate ion. And what did the author show you the picture? For every 2 potassium ions, you get 1 chromate ion. You get that? That's what he keeps wanting to do. And that's the hardest part of this chapter. So those things are really ions floating around. And what about this guy here? What's going to be in this beaker? For every 1 potassium ion, there's going to be what? This is important. I know you can do this. What's in this beaker? Did I say potassium? I meant barium. Sorry. For every 1 barium ion, there'll be what? 2 nitrate ions. That's what's floating around here. Get that? Now they're going to bump around, bump around, bump around, bump around. Now, let me ask you this question. What happens when the potassium bumps into chromate? Oh, it'll make potassium chromate. No, it won't, because it's in water. So they bump in, and no, sorry. Water's ability to pull you apart is greater than your ability. So if potassium bumps into chromate, it's not going to make a solid potassium chromate. But what happens when barium bumps into nitrate? Nothing. Bump, bump, bump. What if I put them together? Now look at the next picture here. What if I put them together? Now I put all the ions together in the same beaker. Now what? What's that? What's that right there? What is that? And again, when I give you your own copy of this, I'll give you your own copy here tomorrow. See that? You'll be able to look at that chart, and you'll say, did you know that barium chromate is insoluble in water? What does that mean? When barium hits chromate ions, what's it going to do? Boom, boom. It's going to form a solid. What's the driving force? Elizabeth, what's the driving force? We only know a 4 right now.
Hydrogen bonding.
What is it?
Hydrogen bonding.
Oh, that was a good answer a while ago. There are 4 driving forces, and we went around the room. One of them said formation of a gas. Somebody said formation of water. What was another one? What?
Transfer of electrons. And
It could have been transfer electrons, but not in this case. There's one more left.
formation of a solid.
Yes. Okay, now, so in this case, there was a formation of a solid, and here's a fancy word, and every chemistry student knows this word. What do you call an insoluble product? An insoluble product, that's going to be a solid that falls to the bottom of the beaker, is called a precipitate. It's a precipitate. Okay, now, it is true, if you watch The Weather Person, that we have all kinds of water on this planet. We have water in lakes, water coming out of my faucet. We have water in the air. We have water in clouds. Now, a lot of times that water is where it's supposed to be, but sometimes the water that maybe is up here, sometimes it bumps into each other and gets bigger and bigger, and it gets so heavy that it falls. And when it falls out of the sky, what do you call rain and sleet and snow and hail? Precipitation. Oh, I like that word. What do you call it in chemistry when you have a solid and it gets to a point where it falls to the bottom? Also, it's called a precipitate. This is a precipitation reaction. You get that? What was the driving force? The formation of a solid. And by the way, if you were to look up on that chart, again, I'm sorry I didn't have you in today. What about potassium nitrate? If you look over there on that chart, it'll tell you that potassium nitrate is soluble in water. That's why it didn't come out in the form of solid. It's still floating around like ions. Here's a question I always ask on a test. If you react those chemicals together, what product is going to be the solid? I will give you a chart. You'll look on the chart, and you said it's going to be barium chromate is the solid. And then I'm going to ask you the next question. Will this liquid here still be an electrolyte? Will this liquid here still be an electrolyte? I keep looking at your faces because I'm looking at you. All right. How about John? What do you think? Will this still be an electrolyte? Yes or no? What do you think? If I stuck those two wires in here, do you think it would conduct electricity? Why? Okay, that's fine. Thanks for being honest. What do you think, Max?
Yes, because it's still like the salt water.
I mean, it's not table salt water, but it's still, the water still has ions in it, doesn't it? So, see these ions here? They're still in there, aren't they? They're still floating around. So it still would be an electrolyte, even though a lot of ions formed a ionic compound that fell at the bottom. All right, one more time. When you react this chemical and this chemical, and they both are aqueous, so it looks like two beakers of water. You put them together, and all of a sudden a solid forms and eventually falls to the bottom. Okay, what do you call an insoluble product? Precipitate. Okay, so that means this is a precipitation reaction. You get that? What was the driving force on the precipitation reaction? Formation of a solid. That's exactly right. You get that? Okay. Now I want to show you that the author, and I'm okay with this. Many chemistry teachers do this because they had a chemistry teacher made them do it. I'm not going to do this, but see these little rules here? It tells you, they want you to memorize these rules. I'm going to actually give you a chart and let you use it on the test. You get that? And when you get that chart in your hand tomorrow, you'll see what I mean. But here's what they'd like you to memorize. Most nitrate salts are soluble. What do you think sodium nitrate in water? You think sodium nitrate would dissolve in water? Is sodium nitrate a salt? Remember, a salt's an ionic compound, right? Is sodium nitrate a salt? If I put sodium nitrate in water, would it dissolve? Yes, it's a nitrate, isn't it? How about potassium nitrate? Yes. How about ammonium nitrate? Yes. Iron nitrate? Yes. Almost every nitrate I know of, it dissolves in water. It's soluble. So it's not going to be precipitate. How about number 2? Most salts, so sodium and potassium and ammonia, are soluble. What about sodium sulfate? Soluble. You won't see it. How about potassium chloride? You won't see that. It'll dissolve. How about ammonium acetate? You won't see that. It dissolves. And I don't mind if you want to try to memorize these, but I actually will give you a chart, and we'll see that tomorrow, okay? All right. Any questions? All right. I know it's kind of a hard class today, but I think